So hey everyone, in this video we will discuss about our assignment topics, that is conduction in spherical coordinates with generation in steady microscopic balance. So our first question is here. We have to derive the conduction in spherical coordinates with generation by cell balance method and equation of change method. So first part we will do by cell balance method. So we consider a thin spherical shell and inner radius r, and the outer radius of this spherical shell is r plus delta r, and the surface area at r is at inner radius, that is 4 pi r square, and surface area at r plus delta r, that is a r plus delta r is equal to 4 pi r plus delta r का whole square. So the volume of this cell, differential cell, is nothing but 4 pi r square delta r. So for the steady state system, the energy balance look like the rate of energy in minus rate of energy out plus rate of generation, and the accumulation will be zero. The input minus output plus generation minus consumption equal to consumption accumulation. For the steady state, the accumulation will be zero. There no consumption, so that would be also zero. So our equation will look like as a rate of energy in minus rate of energy out plus rate of generation equal to 0. So we consider QR be the heat flux and Q be the volumetric heat generation rate. So the heat flow in the spherical shell at r, nothing, r is equal to 4 pi r square into QR. Now the heat flow out at r plus delta r equal to 4 pi r square QR, and the heat generated in this cell is 4 pi r square delta r dot q. So we substitute our equation in this equation, substitute the value in this equation, so we will get our final equation, that is 4 pi r square q r minus 4 pi r square q r plus delta r plus 4 pi r square delta r into q naught. So divide the whole equation by 4 pi delta r, so that will look like as. So by using the differential definition of the derivative, we will get our equation like that: d minus d by dr r square q r plus r square q equal to 0. After that we simplify this equation and we will get 1 by r square d by dr into r square q r equal to q. So now apply the Fourier's law for heat conduction, that is qr minus equal to minus k dt by dr. So the value of qr we will put on this equation here. So we will get our equation like 1 by r square divided dr r square minus k dt by dr equal to q. So assume thermal conductivity, that is k, is constant. So our equation will look like minus k by r square d by dr r square dt by dr equal to q. Now rearranging the standard form of the for the steady state temperature distribution in spherical coordinate is k by r square d by dr r square dt by dr plus q equal to 0. This is our final answer for conduction in spherical coordinates with generation. So now by in part 1 we will derive this equation by equation of change. So the general form of the energy equation in term of temperature t for the stationary solid where velocity v is 0 is rho cp delta t by del t equal to minus del function dot q plus q generation. So where rho is density and cp is specific heat capacity, q is heat flux vector, and the q generation is volumetric rate of heat generation. Now apply the steady state and Fourier's law. We know that for the steady state process the temperature doesn't change with the time, so the temperature will doesn't change with the time, so the dt by dt function will be 0, that is written here. So negative gradient of temperature will look like q equal to minus k into del t. So substitute this into our energy balance, that was equal 0 equal to minus ka del function dot k minus k delta t plus q generation. So by simplify we will get this k del square t plus q generation, where del square in spherical coordinates is r theta is defined as, so that here r theta phi is the dimension of the differential shell. So del square t will look like 1 by r square del by dr into r square dt by dr plus 1 by r square sin theta del by d theta sin theta dt by d theta 1 plus 1 by r square sin theta d square t upon d phi square. So substitute that del square t again in that equation, so we will get our equation that will look like that. So most of the microscopic valence involving space view assumed symmetry where temperature varies only with the radius r. So in this case the derivative with respect theta and phi will be 0. So the k by r square d by dr r square d theta t by dr plus q generation equal to 0 we will get from this equation. What we will get from this line, we will get our final equation, that is k by r square d by dr r square delta t by dr plus q generation, because here the differentiation of the theta and phi will be 0, so the d by d theta term will be 0 and this term will be also 0, so only this term will be remaining and this term will be remaining. So our final equation will look like k by r square d by dr r square delta t by dr plus q generation equal to 0. So here we have done with our derivation of conduction in spherical coordinates with generation. So now we will do numericals on this topic. So our question is, a hollow sphere has inner radius ri, that is 0.05 meter, and outer radius r naught equal to 0.15 meter. Heat generation 2 into 10 the power 6 watt per meter cube. Thermal conductivity 10 watt per meter Kelvin. Inner surface is insulated. Outer surface temperature is 120 degrees Celsius. So that is a sphere. So the inner surface of this sphere is insulated and outer surface temperature is 120 degree Celsius. So we have to find here the temperature distribution and maximum temperature and its location and total heat transfer by equation of chain method. So we know our final equation we will get this equation k by r square d by dr r square dt by dr plus q generation. So we now simplify this equation by we will get d by dr r square dt by dr equal to minus q r square by k. Now we integrate this equation, we will get r square dt by dr equal to minus q r cube by 3k plus c1, that is constant. Now Rearranging this equation, we will get dt by dr equal to minus qr by 3k plus c1 by r square. Now we have to find here the constant value, that is c1. So first we will apply our boundary condition, that is given above. Means the inner surface of this sphere is insulated at the inner surface ri, that is 0.05 meter. The heat flux is 0 because there is no heat inside the surface, because that is insulated surface. So dt by dr ri equal to 0. So our equation, this equation will become like that. So q ri by 3k plus c1 by r square. We simplify this equation, we will get our c1 constant minus q ri q by 3k. So now again v dt by dr equal to minus q r1 by 3k plus c1 by r square. Now we integrate this equation again and we will get our equation like dr, that is function of radius r, equal to minus q r square by 6k minus c1 constant divided by r plus c2, that is another constant we will get by the differentiation, by the integration, sorry. So substitute c1 that we have found above. So substitute c1, so our equation will look like dr minus qr square by 6 minus qr cube divided by 3k plus c2. So our another task, we have to find here the value of the constant c2. So we apply the our second boundary condition, that is surface temperature at r equal to r naught, that is given 120 degrees celsius at outer surface. So our outer radius is 0.15 meter and the temperature at the outer surface is 120 degrees celsius. So we will put our values in this equation. So we will put on this values in this equation. So we will get our c2 value, that is 925.56. so we 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 found c1 and c2. So now we have to find our final temperature distribution, that will look like as a tr 33,333.33 r square minus 8.33 r plus 925.56. That will look like our final temperature distribution. So now in the second part, we have to find the maximum temperature and its location. So in a system where one boundary is insulated, and that maximum temperature always occur at the insulated surface because the temperature gradient is 0. Their location r equal to 0.05 meter. So we have to find calculation. We have to find T max maximum and its location. So the location of that T maximum is Ri, that is inner surface 0.05 meter, and we have to find the maximum temperature, that is 675. That will get by putting the value of Ri, that is 0.05. So we will get our maximum temperature, that is 675.56 degrees Celsius. So our last part for this question is total heat transfer rate we have to find. So at steady state, the total heat leaving the outer surface must equal the total heat generated within the volume of the whole space. For the whole space, जितनी हीट आई उतनी ही हीट जाएगी in minus out for the whole sphere at steady state. So we know the volume for this whole sphere is v equal to 4 pi by 3 r naught q minus ri q. Here r naught is outer radius of the whole sphere and the Ri is for the inner radius. So we will put the value. We will get our volume for this hollow spherical cell, that is 0.01361 meter cube. So now we have to find the heat transfer rate, that is Q is equal to Q dot V. So Q is nothing but 27227.1. Heat is already given in this question and volume we have find here. So here we have finished with our numerical and last part of this question, that is total heat transfer rate, that is 27,227.1 watt.